the INET 2017 conference, which is focused on students and student talks. So this morning we are going to have 2 lectures, and first of them is going to be given by Professor Kellner from University of Oxford.
Okay, good morning. Now, I should say that this talk is going to be really a very introductory talk. It's a talk that one might get at the beginning of a lecture course in relativistic fluids and applications of them. Because I've got 55 minutes, this of course is not going to be all of the lecture course. It's just first steps in it. But I think sometimes it can be useful to focus on these first steps for a bit, because in everyday work with these equations, one gets into much more complicated things, and sometimes people are not quite familiar with some of the basics. So this talk is really, really basic. I'm not going to be talking about applications of hydrodynamics at all in this talk. It's just about some basics. I'm also going to be specializing it to talking just about the simplest sorts of fluids. These will all be perfect fluids. I don't have any viscosity, they're not radiating, there aren't any magnetic fields. This is the basics. And then the other things of relativistic hydrodynamics, one builds on top of that. I'm really, that's what I'm concentrating on. Now, to advance slides, do I do that with this, or
Yes,
do I do it on here?
It should work.
Okay. Oh, I see. Right. Good. Thank you. Right. Let me just practice this. Be careful I don't forward several slides at once. Okay, I want to first of all say some things about going from Newtonian theory to special relativity, which I'm sure you all perfectly know, but I'm going to repeat them so that we've got them in our minds. Because the way that I'm going this morning is I'm starting off that we know something about Newtonian fluids and how they work. What is the transition that one makes in going to relativistic fluids? What are the steps? What are the important things in it? Now, in going from Newtonian theory to special relativity, we are going, of course, from 3-dimensional space plus time, which were seen as being quite separate things, classically, to 4-dimensional space-time, in which the dimensions of space and time are brought together into a single continuum. And in doing this, we go from an interval, the distance between 2 points in a 3-dimensional space, so what we've got here, to talking about an equivalent distance between 2 points in a 4-dimensional space-time. We gain the time part. And that distance between 2 points in space-time is an invariant under coordinate transformations. But we do need to always remember that we're in 4-dimensional space-time now and not in 3-dimensional space, and where we're considering the time as being something which is quite separate. Now, if we are in the rest frame of an observer, and we're looking at what is the interval between 2 points in the space-time as seen in this rest frame, in the rest frame, there is no movement. If I'm in the co-moving frame of the particle, I'm moving with the particle. If I use the reference frame fixed with the particle, I have no motion with respect to that reference frame. So the only bit that I have left of the interval is the time bit. It's the c squared dt squared bit. And under those circumstances, where I'm in the co-moving frame of my particle or my fluid element, then the time that is measured by that observer is the proper time. It's the time of the co-moving clock. And one has to keep on making reference to that time. That is the time which is an invariantly measured quantity. If I go into some coordinate system and I have a coordinate time, then that is something which is not an invariant. I change to a different reference system and that measure of time changes. But the time as measured on the clock moving with a co-moving observer, that is something which is an invariant. So we will keep on having to make reference to that. Now suppose I go to a frame that is not the co-moving one. This x, y, and z here, this is represented, I'm going to use for this bit of it, Cartesian coordinates. Go away from that in a minute. This is not the co-moving frame, this is some general frame. But when I'm talking about movement with respect to that frame, I have this relationship between the time as measured on the clock of the co-moving observer and the time that is fixed in my reference frame. So my co-moving time is the tau, the proper time, and this t here is the coordinate time with respect to the reference frame. I need to be able to transform in between the proper time and the coordinate time. And the relationship that I have is this. If I divide all through this expression by dt squared, then I have that the tau d proper time by d coordinate time squared is given by this. Just dividing all through by dt squared. By c squared, dt squared. Now that thing there, of course, is just the velocity divided by the c squared. So here I have that d tau by dt all squared is 1 minus v squared over c squared, and out comes the Lorentz factor. The Lorentz factor is this upside down and square rooted, and dt by d tau 1 over the square root of 1 minus v squared over c squared, which is gamma, which is the Lorentz factor. Lorentz factor tells you how you transform in between proper time and coordinate time. The last thing, or last couple of things that I have to mention here before getting on to the hydro, firstly about the position vector in special relativity. In Newtonian three-dimensional space, I have a three-dimensional position vector. Again, I'm using Cartesian coordinates for the moment here. And I have that my position vector is just my x, y, z. In special relativity, there are two different choices that one can make. One of which is very frequently made in special relativity and is hardly ever used in general relativity. The other is the general relativistic one. And the point is the following. If I come back a slide, we had here this minus c squared dt squared. We have a plus dx squared, a plus dy squared, a plus dz squared, and a minus c squared dt squared. This is an indefinite metric. There are not all pluses in front of these squared terms. Now in special relativity, it can be a good idea to do a trick to avoid having this indefinite metric. And that trick is to use, instead of t, an imaginary time. And in that case, we get back to this, where we have our positive definite metric again. And as our time coordinate, instead of using t, or c times t, we use I times that. And the I gets rid of the minus that we had there. In that case, we have our position vector is x, y, z, I, c, t. And conventionally, the time part of this is written as the last component. The other alternative that you can make is to say, no, I don't want to be involved with an imaginary time. I want to be using a real time. In that case, I have to live with the indefinite metric. I have my position vector being x, y, z, and ct. This looks more natural, but it comes at a price. It means that I already have to introduce the idea of a metric tensor. The coefficients that come in front of the dx squared, dy squared, dz squared, dt squared, I have to keep track of the fact that I have plus 1, plus 1, plus 1, minus 1 there. So I already need to have the Gij, the metric tensor. The first of these is very often convenient in special relativity because you can then use the well-known ideas of classical Cartesian tensors and just put it into 4 dimensions. And we'll see in a minute an example where this is particularly useful. When you go to general relativity, people hardly ever use an imaginary time. There is an exception to this, and there are some old textbooks that still do it. Point is, when you go to general relativity, you have to have a metric tensor. So you don't gain in that sense by the trick of using an imaginary time. The place where you may want to do it is if you are quantizing. And then it can be very, very useful to have a positive definite metric. And people use the imaginary time for that purpose. But in standard general relativity, it's now no longer done, or it was in the early days. But for this next bit here, I'm going to use the imaginary time. Then I'm going to switch. Okay, the last thing I have to say about background special relativity is to mention the principle of special relativity, the idea of covariance, that physical laws need to be the same in all inertial frames. It doesn't matter how you're moving from one inertial frame to another, you should have the same content of your physical laws. This is the idea of covariance. But in special relativity, it's a limited family of observers for whom this is so. It's the inertial observers, family that are all moving constant velocity relative to one another. If you have accelerated observers, that can be treated to some extent in special relativity, but for the full story, you need to go into general relativity. The thing of covariance in the framing of physical laws is guaranteed if we use, for framing those laws, scalars, vectors, and tensors, as long as they have the same dimension as the space. In other words, 4 dimensions of space-time. There is an equivalence here with making rotations in a 3-dimensional space. If you have one vector equals another vector, and you look at this in one frame, if you then rotate your coordinates of that frame, all of the components of the 2 vectors are going to change. But if the first vector is equal to the second vector in the first frame, it will still be equal to the second vector in another rotated frame. And this is the point about using these quantities, all of which have that property under transformation. Okay. Yes. Right. This is the last thing I need to say before moving on to the hydro. Velocity in special relativity. We need to get to a velocity vector. We have a position vector. In order to get a velocity, we need to differentiate our position vector with respect to time. But if we're going to produce a vector by differentiating the position vector, we can't differentiate it with respect to a component of the position vector, the standard coordinate time, because that gives us a peculiar quantity which is not a vector, it doesn't transform as a vector. We have to differentiate with respect to something which is a scalar. And we have a scalar time, it's our proper time. So to get to our full velocity, velocity useful for relativistic purposes, we differentiate the position vector with respect to proper time. Now, in order to make contact with Newtonian velocities, three velocities, we would like then to transform this to talking about Newtonian coordinate time. So what we do is we put in our dt by d tau, which was our Lorentz factor, and then we have that d by d tau is equal to d by dt times dt by d tau. And that produces then our fourth velocity, which is given by this. And that's the quantity that we need to use in framing our relativistic expressions. Okay, so that's the background. Now I wanted just to remind you about these things and how they come in a systematic way. Now we're going to move on to the hydrodynamics. Now, I'm starting off here wearing a Newtonian hat. We're going to go through to talking about special relativity and then general relativity. Go through the steps from the Newtonian theory. I can't do all of that in this hour. It takes longer than an hour to do that. But I'll go through the first steps of it so that one can see the principles which are coming into it. Now, I know that a lot of you are going to be familiar with quite a bit of this. But quite probably everybody here is going to see something that they don't quite appreciate in some way. They haven't quite got. So it's worthwhile paying attention, even if you think that you know all this stuff pretty well already. I apologise to people who do know it well already, but sometimes it can be very interesting to see these things brought forward step by step. So for deriving fluid equations using my Newtonian hat, I have these three principles. I have conservation of mass, I need an energy equation, and I need a momentum equation, an equation of motion, which is the Euler equation here because I'm dealing just with perfect fluids. And my question here, which I'm addressing, is how does relativity theory differ from Newtonian theory in this, in the implementation of these three things? I'll start off with the conservation of mass. Now, what I want you to do here is to think about a little fixed box. My fluid can move into the box, it can move out of the box, but the box is fixed with respect to some reference system. And my box is going to have unit volume. And that means that the amount of mass that I have in the box, since it has unit volume, is the same as the density of the fluid. And the density is rho. I'm in Newtonian theory, so there's no ambiguity about what I mean by the density. Density is mass over volume, and we only have one conception of mass. Now, if I want to know how the mass in the box is changing with time, I have this relationship in between the d rho dt, which tells me the increase with time of the mass in the box, and the rate at which material is diverging, is flowing out of the box. that rho dt is the increase of mass in the box is the negative of the rate at which matter is flowing out of the box. So this is very, very basic. I'm now going to write this out in components using still, for the moment, my Cartesian coordinate system. In components, I have this. Now, the next step is that I'm taking all of this over onto the left-hand side of my next equation. So that I have this. And I have plus, 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 plus. Also, for the time one, I have a plus. Then I do a trick. And the trick is extremely non-obvious in Newtonian theory. Although, since we know about relativity, it may not seem so peculiar to do it. What I'm going to do is, with the last term here, the d by dt of rho, I'm going to multiply and divide it by I times c. I times c is a constant, so I have no difficulty about putting my IC here after my d by dt, and also down here. IC is a constant, so I can do that. So then, having put that into there, I then get, I can rewrite this one with that, like that. It's a sum over my 4 dimensions. And this is a very compact form. With these definitions, that I have my position vector, and I'm now writing my vectors like this in this index notation. I have my position vector being x, y, z, I, c, t. I have my Newtonian velocity, so no gamma factors here. My Newtonian velocity, I have 4 components. It's a funny velocity. It's got a 4th component. I'm defining it like that. Vx, vy, vz, I times c, which is partial d by dt of the position vector. Now, this is exactly Newtonian theory. This is not relativity. It's Newtonian theory written in an unusual way, with unusual definitions, with fourth components here in these vectors. I'm free to do that if I want to. Now we think about going to special relativity. Notice this is a beautiful compact form. Very nice. Now I want to go to special relativity, and what do I have to do? Now, an immediate problem in going to special relativity is that having this definition of velocity, as we were saying a minute ago, is no good. Because my t here is actually a component of a vector. And this is just a formal thing that I've done here in Newtonian theory. Because if I wanted to take this as a serious 4 vector, then I'd better not be differentiating with respect to coordinate time here. So I have to go to doing what I did with the 4 velocity. I take my derivative of the position vector with respect to proper time. In fact, here, although I've written this as a partial to make it look like that, it actually becomes an ordinary derivative. And so I now need to use my 4 velocity here instead of my 3 velocity. And this makes the velocity a 4 vector, as is necessary for covariance. So the principle of special relativity is coming in here. I'm demanding that for framing physical laws, I should be able to do this in a covariant way, and I know that I am guaranteed in that if I use scalars, 4 vectors, and 4 tensors. So I want to use only those sort of quantities. That's one key change that I have to make. There's another key change which is sort of hidden here. And that is that I now have to be careful in what I mean by mass. The quantity rho, which I could just say before in a loose way was a mass density, I now have to say what I mean by that. I need it again to be an invariantly defined quantity. And what is the invariantly defined measure of mass? It's the rest mass. It's the mass that is measured in the local co-moving frame. So this rho is now going to be the rest mass density. It's not the quantity that is related to the moving mass in special relativity. That's another thing. Now here I'm going to be using the notation, literature is mixed in this, that rho for me is always going to mean a rest mass density. It's not going to mean an energy density. I'm going to use something else for that. Large part of the literature uses rho as an energy density and puts a 0 subscript on it for a rest mass density. I think that is quite awkward, and I prefer to use rho for a rest mass density and quantity which I'll call E for an energy density, and that's what I'll do. Okay. Now, we've got this. We're needing to write it in terms of these quantities, put through into this relativistic form with 4 velocity and with the rho meaning a rest mass density. So here we are. I've now rewritten what I had in Newtonian theory, putting in my 4 velocity. Apart from that, this expression is the same. I've done the minimal amount that is required in order to make this covariant expression. How we introduce this notation of using the summation convention. So I don't have to keep on writing sigmas. Wherever I see a repeated index, I sum over it. I also use the shorthand notation for partial derivatives. Instead of writing d by dxi all the time, I put comma I. And my mass conservation equation, then I can write in that very nice compact form. And that is Lorentz covariant for flat spacetime. I haven't gone to a curved spacetime yet, which we need to do for general relativity. The way of saying this expression is that since we have a conservation of rest mass, the principle that we have here, of course there can be some circumstances, exotic ones, in which rest mass is not conserved. In that case, we can't use this simple expression. But a way of saying this is that the divergence, the 4 divergence of the flux of the mass is equal to 0. If I take mass from somewhere, it has to end up somewhere else. I can't create or destroy it. That's what this is saying, that my divergence, 4 divergence of the flux is 0 since the quantity is conserved. Okay, now what about curved space-time? Curved space-time going to GR, there's another important thing that we need to do. When we go to GR, it's no good anymore using our partial derivatives. So I say it's no good. We can still use partial derivatives if we want to, and we do. But in order to frame our physical laws, this is not giving us something which is covariant. In order to make our derivatives covariant, we have to go to this generalized form of derivative in our curved spacetime, which is the covariant derivative. And that we write with the semicolon. So again, making the minimal difference to our conservation equation. The thing that we have to change in going to a curved space-time is to replace the comma that we had before there, this comma down here. We have to replace that by the semicolon for a covariant derivative. And that expression is then generally covariant, curved spacetimes for general relativity. Now, another change that I've made there is that I've gone from using I as an index, ijk, when used in special relativity, to using Greek indices. And I'm also going now to make this change, stopping using the imaginary time and going over to using a real time. Because now that I'm going into general relativity, I have to have a metric tensor anyway, and it is convenient to go to having time as being a real quantity. Okay. Now another step that I have to make. I'm spending a lot of time here on the mass equation, but this is an important prototype, and there are various concepts come in here. Now take that, and that's a product. I expand out my derivative of the product, which I can do with covariant derivatives in exactly the same way as I do with partial derivatives, differentiation of the product. So expanding out the differentiation of the product, I can write this as u mu times the derivative of rho, and the derivative of rho is the same as a partial derivative as it would be for a covariant derivative, because rho is a scalar quantity. And then my second term plus rho times the covariant derivative of the four velocity. That equals 0. Now this first term that I have here, my u mu is a four velocity. It's dx mu by d proper time. This here, the rho comma mu, is partial d rho by dx mu. So taking those two together, chain rule, I get that. I get d rho by d proper time. And it's convenient to introduce this operator, which is the derivative with respect to proper time. The time as measured by the co-moving observer, the co-moving fluid element. Call that d subscript t. And then my conservation of mass equation I can write in this form. That I have the derivative of rho with respect to proper time is minus rho times this quantity, the divergence of the full velocity, which is telling me about the rate of expansion of my fluid. Now I've labelled this equation by A. I'm going to have three key equations here. This is the first one. So you see we've ended up with an extremely simple equation here from the conservation of mass. But we've had to make a number of considerations along the way in getting to this. And these are quite important considerations. Okay. Now we do the next one, the energy equation. Now with the energy equation, we're going from a rather different direction we're again going to have a box, little elementary box, but it's a different box this time. The previous box we had fixed with respect to our reference frame, and the fluid moved through it. This box is not fixed with respect to the reference frame. It's one which moves with the fluid. Now I've drawn it as a rectangular box, but of course, since it's moving with the fluid, its shape can change as well. But this, it's nice to have a little graphic like that to focus attention. So this is a box which is moving with the fluid. And this time, instead of having my box being of unit volume, it's a box which contains unit mass of my fluid. Moves with the fluid. It's more like a bag than a box. It can change its shape as the fluid moves. And it always contains within it the same particles of the fluid. I'm going to focus on this box, and I'm going to think about thermodynamics. First law of thermodynamics, I'm talking about a perfect fluid here. I don't have any means of my fluid changing its specific entropy. I don't have any viscosity. I don't have any heat conduction. I don't have any radiation. I don't have any generation of energy. This is a perfect fluid. So in the first law of thermodynamics, which I am doing focusing on unit rest mass of my medium, I have that the changes of internal energy in my box, I'll call my internal energy per unit rest mass epsilon, would in general be equal to a term that we haven't got here, the TDS, temperature times change of specific entropy. I don't have that because I'm not allowing entropy to change, specific entropy. And all that I have is this term here, which is the term for doing work. And that is P dV, minus P dV, because if I have the volume of my box, V is the volume of the box, if I have that increasing, then the specific internal energy is of course decreasing, and the reverse. Epsilon, internal energy per unit mass. Now we've got unit mass in the box, so that means that rho times the volume of the box is equal to 1 by definition. So the volume of the box is 1 over rho. I put that into this expression, and I then have that changes in specific internal energy are given by minus P times d of 1 over rho. That is straight first law of thermodynamics. Now we make another step. We introduce the total energy density of the fluid. In the case of my perfect fluid, that means that I have two contributions to this. I have the rest mass energy, and I have the internal energy. Both of those go together in the total energy. And I can write my total energy density as this. I have my first term, which is my rest mass density times c squared. My second term, which is my rest mass density times my internal energy per unit rest mass. So I have that my total energy density is rho into c squared plus epsilon. Now notice that this is the place where you make a step from Newtonian theory to special relativity, because we've used E equals mc squared in here. If I was doing Newtonian theory, I wouldn't be talking at all about the rest mass density as being part of the quote generalized mass density. I wouldn't have that. I would only have the rest mass density coming into a mass density. So this energy density has the two bits which come together. Now, I take differences and I differentiate through this. I get dE is equal to c squared plus epsilon times d rho plus rho, c squared is a constant, times d epsilon. I know what the epsilon is. We've just worked that out. So I put that in. It's minus p d1 over rho. And I have that. I then differentiate out the 1 over rho. And I come to this. And I have two terms, both of which are multiplying a d rho. I take the d rho outside of a bracket. I have here c squared plus epsilon plus p over rho times d rho. I'm being a bit pedantic about doing this because it's coming to the introduction of a quantity which is an absolutely key one in relativistic hydrodynamics. It's the enthalpy. That I can now rewrite using the expression for E, rho c squared plus rho epsilon, as E energy density plus the pressure divided by the rest mass density times d rho. So note the appearance of the enthalpy density, E plus P over rho. If I want to take this quantity per unit volume, it then becomes just E plus P. And that quantity, E plus P, you start seeing all over the place in relativistic hydro equations. I should say that a few years ago, there was somebody, I won't name the person, a very eminent astrophysicist, who said to me, I've never been able to understand why I keep seeing E plus P all over the place in equations for relativistic jets. Why is it? This is the reason. And there are a lot of people who are not so familiar with that. Okay, so what I've got here is how a change in energy density is related to a change in the rho, the rest mass density. Now, I've been talking all the time here about a co-moving element of fluid. So I can, of course, talk about these as changes which are happening in some time span as measured by that co-moving observer. So I can change these into derivatives with respect to proper time of the co-moving observer. And here I have my final form of the energy equation. dTE is E plus P over rho dt rho. Again, an extremely simple looking equation. And that I've labelled B. It's the second one of my set. And if I want to put this in terms of more fundamental quantities, I can substitute in here for the dt rho from the mass equation. Okay, we've got two of our three equations, and now we've got the third one. Now, the third one is the most complicated one. It's the momentum equation. And here, I don't have time to go through all of the business about this. If I had another hour, then I could tell you all of the details about this. But I'm just going to give you this little bit of outline. Now remember that at the beginning, or near the beginning, when we were talking about conservation of rest mass, I said that the conservation of rest mass equation one can represent in saying that the flux of the rest mass out of a box satisfies a conservation equation. The for divergence of the flux is 0 if I have a conserved quantity. Now, momentum, of course, may or may not be conserved. But let's think about it as being conserved for the moment, and then we'll think more about that in a minute. If I want to talk about conservation of momentum, I can learn from the experience that we had with the conservation of rest mass and say, well, if I've got a quantity just being conserved, I should be able to write an equation like this, where I have the density of the quantity that I'm talking about multiplied by the force velocity. And I take the covariant derivative of that lot, and it should be 0. This is exactly a similar thing to what we had with the rest mass. But we're going to investigate what happens when we put some more complicated quantity in for the x. And the quantity I'm going to put in here, it's got to be the density of the quantity that I want to be conserved. I'm talking about momentum, it's momentum density. And it has to be the form momentum here, defined, so form momentum would be the rest mass times the force velocity. It has to be rest mass, not if this is a suitable vector quantity. And here I'm talking about the density of it. So it's a rest mass density here. Let's see what happens if we put that in for x. Now, what I have is this. I've just put in rho times u mu in here. Now, I'm again going to expand this out as a product. I'm going to take rho times u mu as one part of my product, and the u mu as the other part. And what I'm going to differentiate this one first, leave that one, then the reverse. So I've got the covariant derivative of u mu times rho u mu plus u mu times the covariant derivative of rho u mu. Well, the second one is 0 because that lot is just what we had equal to 0 in the conservation of rest mass. So if we're conserving rest mass, that second term is 0. So what I'm left with is just this. Now, at this point, I'm going to skip some things, which I might say if I had more time. This quantity here, which is the contraction of the covariant derivative of the force velocity with the force velocity, is the force acceleration, a mu. Now, the way that one could look at this is that the force velocity is a unit tangent vector along the world line of the particle that I'm talking about, the fluid element. So what I'm doing is I'm projecting the covariant derivative of the force velocity along the world line of my particle or fluid element. And when I do that, I get the force acceleration. Now, that quantity is equal to 0 if there are no forces acting. Remember that in general relativity, gravity is not a force. It's a property of the space-time. So here I'm talking about other forces, if you like, real forces that may be acting on the system. And if I'm talking about a fluid, a very important one of these forces is pressure. Of course, all sorts of other forces that could be acting. Here, I'm specializing to a perfect fluid, so the force that I'm talking about is pressure. Now, if I have forces acting, this is not zero, and I have some expression there which is giving me a density of 4 force. But if I do take that I have no forces acting, then this is 0, and then I do get conservation of my form momentum. Now this makes perfect sense. Momentum is only conserved if I don't have the action of forces. Forces change the momentum. So it's fitting perfectly well. Now if I don't have any pressure in my system, I'm talking now about my fluid, if I don't have any pressure, then I also don't have an internal energy. And my energy density is just the rest mass energy. So I can just replace the rho that I had before by the energy density under those circumstances. So my expression then for my conservation of momentum would be that thing equals 0 with rho replaced by E. Now, of course, sometimes one is interested in pressureless fluids, but most of the time we're not. So what does one do? It would mean that we got left here, imagine this with that being E. We have an expression here involving the pressure, which is telling us how the forward acceleration is working. And that's a bit of a mess. We would prefer not to have that. And so there's a nice trick that one can do in generalizing the expression that you have in here, so that you take the expression involving the pressure from the right-hand side over on to the left-hand side, and you get a generalized expression in here. And that is this one for a perfect fluid. So you've gone from taking rho, u mu, mu mu as the thing that we had inside that bracket. We've gone from that, we've generalized by taking the rho to an E, but then we have got P coming in as well here. So you see the term E, u mu is sitting in this. E, u mu. But we've also got a bit that is involving the pressure. Now, with that generalized form, you can replace the rho u mu in that conserved bracket by the T mu mu, and you get this, which gives you conservation not only of the classical momentum, but also of the classical energy, both of them. You can look on it that you have 3 components which tell you about conservation of momentum, and another component which tells you about conservation of energy. But we've already got an expression for conservation of energy that we got from something very, very fundamental. It's the first law of thermodynamics. So, using that fact that if we take this, it includes also the concept of conservation of energy. We can project this along the world line of the particle or of the fluid element. And that precisely gives us the local energy equation of the co-moving fluid element. It's exactly what it is. And so one gets the form of the T mu mu, the energy momentum tensor, by demanding, take the most general form that you can for this tensor. One that has the most general possible things to multiply p by. And you then say, I demand that the equation that I get should reduce to the first law of thermodynamics. That gives you a unique form for the energy momentum tensor, if it's perfect fluid. But that's a little bit intricate going along the way to that. While the steps of it are actually quite interesting, I don't have time to do that now. So, the form for T mu mu up here can be systematically derived by using this reduction of this bit of the momentum conservation equation to the first law of thermodynamics. Okay, so it contains that bit. It contains the energy equation. It also contains the momentum equation, the equation of motion. Here we are. This is my general conservation expression. It leads to the Euler equation, after I must say that's a manipulation. And I'm just going to give the final form that you have for this. I can again write this in terms of my operator dt, the derivative with respect to proper time, co-moving with my fluid element. And I have this expression. Now, this is my third equation. I'm calling it C. Equations A and B were extremely simple in form. This is more complicated in form because at this stage we see explicitly some information about space-time entry. And it's entering because I have the metric tensor sitting here, and I also have the Christoffel symbols. I need to know what those are in order to implement my system of relativistic hydro equations. The systems I've got, the mass equation A, the energy equation B, the Euler equation C, they form the full set of hydro equations. And they are totally, totally general. I haven't said anything about symmetries or the nature of my space-time, nothing. They've taken a particularly nice form because I've worked in the co-moving frame of my fluid. Frequently one wants to implement them in some other frame with respect to which the fluid moves. But then you just have to transform these equations to the other frame. So these are general equations. We then need the Einstein equation to tell us about the space-time geometry. And that's the end of the story for today. I've come magically to 0 on the clock. So that's it. Does anybody have anything to put on?